And the next one is our presentation, our paper presentation. The title is Transformer-Based Text Detection in the Wild. And I want to ask whether the audience is, whether the paper writer is here. Yep. Okay.
Yeah.
Great. Yeah. Please go ahead with your talk. Yeah.
Yeah. Thank you. Thank you. Let me to. Yeah. Let me. Okay. Can you see my screen?
Yep.
Yeah. Hello, everyone. I'm Zubair Raisi, and welcome to my presentation on transformer-based text detection in the wild. This is a joint work with my supervisor, John Zelek, and my colleagues, Mohammed, George, and Steve. And the task of syntax detection or text detection is to find and localize text instances in the given input image. And text detection is a primary step for syntax recognition, and accurate or precise text detection or could lead or provide a better recognition result at the end. But syntax detection is challenging due to text diversity, that is, there are lots of arbitrary or oriented type of text that appear in the wild images, the complexity of scenes, and some distortion factor that affect to the performance of detection. And text also can be occluded like objects that we actually at the end can get a different performance. In recent years, many syntax detection frameworks or architecture mostly inherited from object detection frameworks. And we can categorize them into two main categories: segmentation-based and regression-based. In segmentation-based methods, like object detection, they are try to classify each pixel of the input image and to create a mask at the end, and then use some aggregation algorithm to create the output result. But regression-based methods, on the other hand, try to directly output a bounding box around the text instances by using some mathematical computation, and they are much more faster than the previous one. However, these frameworks have some problem or challenges or some drawbacks, like they have a complex architecture, they contain lots of multiple stage post-processing like in segmentation-based methods, or they have geometric priors like non-maximum separation or anchor design that actually have a at the end could to make the training hard. In contrast, in this work, we try to utilize a recent architecture end-to-end object detection using transformer, and we utilize or leverage that architecture for syntax detection. And our contribution here is to make this architecture to work for multi-oriented text that we precisely to draw a oriented bounding box around the oriented text, because the baseline method is only could detect the object in a rectangular shape. So we propose a loss function that is a rotated bounding box loss function that consists of two a small loss function, a loss function for regression that is a smooth LN loss, and a rotated GIU loss that we make the generalized intersection of union that proposed in that paper into rotated version. And as you can see, the rotated version is much more complex compared to the rectangular bounding box. And we use that to detect, to apply to our final architecture. Let's see here an overview of the proposed architecture. So we have an input image, this is CNN that we use a ResNet 50 for extracting the feature of the input image. And we have a 2D positional encoding that due to permutation equivariant problem of the transformer, this 2D positional encoding that are fixed sinuses of different frequencies added to the features of the input image, and they go to the transformers encoder that consists of a multi-head self-attention and feed-forward neural network to give us some encoded features. And in decoded, we have a learned embedding vectors that they are object queries that learn about the location size or other properties of the input image, and those output of decoder goes through the shared fully connected layers that output for us the class, directly the class and the rotated bounding box location of the input image. And at the end, we have a rotated detected text instances of rotated bounding box. For training of our network, we first train the network or the model by combination of two data sets, that they are synthetic data set, and as you can see at the first row, they are just a synthetic data set that we use for pre-training. And for testing, we test our model on 3 benchmark data sets, RCDR15 and RCDR17, that they have annotated in quadrilateral way. And the MSRA-TD 500, it's annotated in a rotated bounding box way. And the RCDR15 has is gathered, it has images, gathers images of, sorry for that. Gather images from indoor location, and the RCDR17 has images from mostly from outdoor location, and it's most challenging compared to the 3 data sets. And it has 9 languages that we can also count that is one of the challenges of this data set. And we test on this, or fine tune and test on this data set. So here we have we compare or propose methods with many state-of-the-art methods, that's are regression or segmentation-based methods, and just by using a prediction head that just output for us a rotated bounding box at the end, or this network or proposed method outperform many of these methods in terms of precision and if measure in these 3 benchmark data sets. And we also improve the performance of baseline methods by a large margin, that the baseline methods use a rectangular bounding box at the output. And as you can see, we improve the results in this architecture by using the proposed loss function or the proposed prediction head. Here you can see the output, the qualitative results of of our model. As you can see, the model could detect many of these texts that, beside of rotated challenges, it also have other challenges that the model could detect precisely those methods. And it's worth mentioning that we also apply or we also tested our model on a unseen data set that is SVT, that is collected from Google Street View. And this method works very well on this data set that we didn't actually fine tune on this particular data set. To see the robustness of the proposed loss function or proposed architecture on rotated text instances, we also get an input image and rotated in different angles, in 4 different angles. And as you can see, the model could precisely detect the text on different orientation here. And in conclusion, in this work, we present a transformer-based architecture for multi-oriented text detection. And we design a new predictor using rotated bounding box to present a better oriented text regions. And for this purpose, we use a loss function that is more precise in measuring the changes in scale and aspect ratios of the detected text regions. And our approach offers a better performance than the state-of-the-art methods in terms of precision and if measured in one of the 3 benchmark datasets. And we also want to thank you, my sponsor, for supporting this work. And thank you for your attention.
Thank you very much for Xavier for your talk. Actually, I have a couple of questions, and the first one is you are using the transformer encoder and later use the transformer decoder and directly. And have you ever tried to first use some typical well-used detections and then use the transformer encoder and the decoder and compare with the performance of directly using transformer decoder and encoder?
We actually didn't use that because we wanted to end-to-end just detect the text just by using this architecture, because in the synthesization, the goal is to just detect the text region by, by a specific architecture. We just, at least in this work, we just wanted to see how this new architecture just work on actually this for text on benchmark data sets. Yeah.
Okay.
But that would, yeah.
Please. Okay. The second question is, we have seen that you have actually a rotation and incorporated in your text detection actually, and you can detect more tight boundaries and across the text, and by rotating your rectangular bounding box. And what about if you have some words that is not really arranged straight? For example, some words that is arranged in a circle or somehow arranged in a trapezoid shape. And have you ever how do you deal with these issues?
Yeah, that's a very good question. Actually, in this work, we mostly, or we only just focus on orientated text, and that's why we use these 3 benchmark dataset, RCDR15 and RCDR17, that they are specifically designed for oriented text, or they have quadrilateral bounding box annotations. But yeah, I know that there are some curved text that they, as you said, that they have curved text instances. But this method, because they just output a rotated bounding box, maybe for those type of text instances, we just get, instead of one bounding box, we may get some 2 or 3 bounding box. As you can see here in SVT dataset, we have a curved text here that it look like, as you said, instead of 1, we get 3, because this is the precisely a way to just output a bounding box for this text by using our rotated bounding box. But for doing of those, we have to just increase the output of our feed-forward neural network to get more points, and in that way we can just get a better representation of text region of this type of text. But as we just actually working on that right now, that to actually for this type of text instances, but for this specific work we didn't actually test on this type of data set.
Okay, great. Another question from the audience, and from Dongfang Liu as well, and he is saying, I'm wondering if you have checked the runtime performance, as transformer-based architecture is parameter heavy. Also, did you perform pre-train for your neural network? And if so, and could you please articulate the precise?
Actually, sorry, I didn't get.
You can also read the
Yeah,
from the chat box. And
yeah.
he's asking basically first the runtime performance, and
the runtime performance for this network architecture is much more faster than segmentation based method. It's about by using one GPU of NVIDIA RTX that we actually tested is 8 gigabyte RAM. We get about 10 frame per second for images, and it's it's kind of slower than most of regression based methods that they actually have a faster or real time maybe detection, but our method is just more accurate in terms of precision and than those methods.
And did you perform pre-train? Did you pre-train on neural network?
Yeah, we only pre-trained on synthetic data set by using just 20,000 of synthetic data set. Yeah.
Okay, great. Maybe the last question, and have you ever tried somehow using the location clues to enhance the detection? For example, if you know that you are on the walking street, that you will detect the text based on okay, this must be something like walking street instead of some restaurant or whatever. Have you tried to incorporate those kind of location information, location clues to enhance the detection result?
Yeah, that's very good question. And honestly, we didn't try that, but we can just use this type of things to better enhance the detection. But no, we didn't actually try that in this work. But yeah, we can just consider that as a future work.
Okay, great.
Yeah.
So I think we don't have further questions at the moment, and thank you very much for your great talk.
Thank you.
We can move to the next talk, and the next talk is HCPO2 and a new human physical fitness action dataset for recognition and 3D reconstruction evaluation. I wonder whether the author is here right now. Yeah, I think Li Xin Liu is here to present their work.
Okay, can you hear me?
Yeah, we can hear you. Yeah.
Okay. Hello everyone, I'm Li Xin Liu from Tianjin University of Science and Technology. Today my topic is a new human physical fitness action dataset for recognition and 3D reconstruction. In this paper, a human physical fitness action feature dataset is introduced, which contains 8,044 action data sequences and 80,414 images. What's more, a new recognition method based on deep learning techniques, including the two-branch multi-stage CNS and LSTM networks with attention are employed to learn the long-term dependence from videos for human physical fitness action recognition on the dataset. And the dataset can be used as the dataset for three-dimension reconstruction. The dataset has the following characteristics. The physical fitness in the experiment contains 3 types, which are push-up, pull-up, sit-up. For each action, the cameras are used for video capture, and one camera is in front and another one is on side. For each action type, both the standard action and non-standard action are captured. The steps to process the data are as follows. Step 1. Record all the action into video files with two cameras. The captured video data is divided into 6 categories. Select one frame from every 6 frames of the video. That is, extract about 5 frames of images per second. Cut out the main part of the human behavior in the picture. Step 2. The captured images are manually annotated, and the sequences of picture marked and the same action is placed in the same folder. Step 3. Make use of CNS to extract the 17 joint features of human body into one-dimensional vector and store them in a file. The extracted information includes the human key points identification, relative coordinates, and confidence, so that 68 elements of information are stored into one-dimension vector, which can be extracted from one single image. Step 4. 10 images are taken as sequences to create the data set. And this picture shows that the sample pictures of the data set and table 1 and table 2 show the amount of each action in the data set and the amount of the data sequences in the data set respectively. The architecture and we proposed architecture we proposed an architecture and the architecture of proposed two-branch multi-stage CNN and the long LSTM attention-based human action recognition method is demonstrated in figure 2. For the spatial dimension, the two-branch multi-stage CNN is utilized to extract the key points filter. The images are first input to VGG19, generating a set of feature maps. The feature maps are input to the two-branch multi-stage CNN. For temporal dimension, the sequences of key points feature works and input to obtain the temporal filters, and the LSTM attention model is applied to recognize the fitness action categories. To evaluate the effectiveness of our proposed fitness action recognition method, the architecture is trained and tested on the dataset. We compared the results of the thorough and traditional machine learning model. It can be found out that the proposed model is much better than the traditional machine learning models. Thanks to the high efficiency of two-branch multi-stage CNN filter extraction, new demo system is constructed based on the proposed human physical fitness action recognition method to show that our approach can be used in practice in real time. The system is tested with the captured video. The results are can be seen in the future. And the upper left corner of the picture shows the probability that this motion is standard. Moreover, we also evaluated two classic 3-dimension reconstruction models on our data set. From the figure 4 and the figure 5, we can find that the data set can serve as the data set from which we can construct a 3-dimension of human physical actions. Thank you.
Okay. Okay. Thank you, Li Xin, for your talk. And I actually have a couple questions as well. And when you do the action recognition, do you find front view and side view which is more helpful in action recognition, or have you tried to use both views as simultaneously to recognize the action? So for example, first one is a front view and another one is side view. Which one do you think is testing is more helpful in recognizing the action?
I'm sorry that I didn't follow you.
Okay, and one is for example, one camera is in the front view, and another camera is on the side of view, and which view is more important, and do you think are more helpful in recognizing the actions?
I think that they are all important because our data sets are multi-view. We use all the data to recognize the motion. So I think that they are all important.
Okay, and another question from Yawen Lu, and how do you extract the key points? And which I think he is referring to the joint points, and how is the performance compared with using transformer or 3D CNN on recognition? And for example, and there's some you mentioned about there will be 16 or 18 joint points. How do you extract those joint points?
We use this model. This model can extract the human joint features.
Okay. Okay. And have you ever tried something like 3D CNN in recognition?
Oh, no, I didn't try.
Okay. Okay. Also, another question is, so have you? I can see later you are actually did the 3D reconstruction actually, right? You model the 3D body of the human. Have you ever tried to use the 3D reconstruction model in recognizing the actions?
Oh, I didn't do it. Yes.
Okay, I think probably you could try later.
Okay.
So one final question is, have you is the data set released already, or it will be released soon? I mean, the data set right now is public or still not public, or later you will make it public soon?
The data set is public now.
Okay. Okay, so we can download from your website, right?
Yes.
Okay. Okay, great. Okay. Thank you very much. I think with this, with finishing of this talk, HC22, and we have finished our workshop. And thank you very much for all the audience, and thank you for all the speakers and our presentation presenters. And thank you for your attention.
Thank you.
Yeah, thank you.